live streaming program of class 11, 12, as well as those aspiring for NEET, JEE Advanced, JEE Main, JEE Advanced, and any other competitive tests after so-called +2 or class 12. Since stereoisomerism is a very interesting chapter, and we need to know for advanced study, we need to know the intricacies of the different aspects of stereoisomerism. Therefore, I thought, why not the class be made public? Welcome, Sami.
Good afternoon, sir.
Good afternoon. So we'll be starting in an auspicious day, the birthday of Messiah Jesus. Merry Christmas to all of you.
Merry Christmas, sir.
Thank you.
Merry
And
Christmas, sir.
thank you.
Merry Christmas, sir.
Thank you. And in this auspicious day, we are starting our stereoisomerism program, for which we are happy. Now, without any delay, I would like to share my screen. I'm using a Santa's cap today. And let me share my screen. And start. And guys who are watching from the YouTube and will be watching in a future time in YouTube must make sure that you are at least good at structural isomerism. Here, stereoisomers have same structure and hence same name, but different spatial relationship between their groups and atoms, for which they are not superimposable. They are not superimposable. Just like your left hand and right hand, they are not superimposable. Someone told me, sir, yes, superimposable. I told you, and I am repeating, that superimposability demands that the two sides should be same. Here the palm top, here the palm top. So when you try to superimpose the palm of one left hand with the palm of the right hand, both lying above, you will not find the fingers superimposing. The pinky is now falling on thumb, and the other side pinky is falling on the other thumb, and there will be a mismatch. Instead, the two are hypothetically related as their mirror images. If you have a hypothetical mirror in the middle, you'll find the left hand is the mirror image of the right hand. So they are not same. Looks like same, but they are non-superimposable. So if any two identical structures, I repeat, any two identical structures having same name but in space they are not superimposable, then they will be declared as stereoisomers. Now this has two parts. Stereoisomerism has two parts. Welcome those who are watching from the YouTube, and make sure that you are at least having basic knowledge in structural isomerism like chain isomerism, position isomerism, functional isomerism, ring chain isomerism, tautomerism, metamerism, these five. And the stereoisomerism has two parts. One is called the configurational isomerism, that belongs to one aspect of one aspect of stereo, and the other aspect is conformational, CONFO, not FI. I am confirming my visit to your house today. It's not that. Conform, FORM, conformational isomerism. In configurational, we need to bond break and bond make. Bond break and bond make at a particular atom called stereocenter. Some people call stereogenic center. And you have to ensure that the molecule does have a stereocenter. Not all molecules, they have stereocenters. So by bond breaking and remaking, I can use the term bond breaking and bond remaking. These are required at a particular stereocenter. That is required. This surgery, as if you are a molecular surgeon, you will be operating on a particular stereocenter, remove two atoms or two groups from their groups in the model and interchange. So bond breaking and remaking, those two things will be required to convert one configurational isomer to the other. But such a thing will not be required in conformational, only rotation about single bonds. And most commonly, such as carbon-carbon single bond, carbon-nitrogen single bond, etc., produces non-superimposable forms, which are stable. I will give you a brief idea on every aspect today before entering into the details of configurational isomerism. So here in conformational isomerism, no bond breaking and remaking is done, are required. Again, configurational has two aspects. One aspect is pertaining to optical activity, optical isomerism. Why the name is given like that? They respond to plane polarized light. I will talk about plane polarized light in details after some time. I'm writing in short, respond to PPL. they are optical isomers. And some that do not respond to PPL. This is about previously it was called geometrical isomerism. Nowadays it is called EZ isomerism. These guys will not respond to any PPL. Plain polarized light will go straight, undeviated, unrotated. But if a particular molecule is showing optical isomerism, then it will respond. Either the PPL will be rotated to the right from the original direction or to the left. Now, these are called diastereoisomers, geometrical isomers. And diastereoisomers are those which have different properties, including physical properties. And most importantly, they are not mirror images. They are not mirror images. Mirror images of each other. And they are not mirror images of each other. Diastereomers, E and Z, they are diastereomers. They are not mirror images of each other. They have different physical properties. Their boiling point, melting point, refractive index, viscosity. Viscosity is almost same, but melting point, boiling point, density, they are all different. In optical isomerism, there can be diastereoisomers, they can be real mirror image isomers called enantiomers. Enantiomers. They are mirror images of each other. And enantiomers have same physical properties, identical, except their response to PPL. The only physical property which is different is except their response to PPL, plain polarized light. If one will rotate to the right, called D or dextrorotatory, plus the other one will be rotating to the left, laborotatory or minus or L. And you can have also a molecule having multiple stereocenters can also have diastereoisomers or diastereomers, which are not mirror images. They have different physical properties. Sometimes enantiomers, particularly, they are significant in biochemical processes. D-glucose that we are taking externally and also in cellular respiration, the D-glucose is combusted, oxidized to carbon dioxide, water, and a lot of energy, so that our body mechanism will respond to D-glucose. The carbohydrate, the starch that we take is converted to D-glucose. The D-glucose that can be digested by cellular respiration. But if you take L-glucose, you can prepare L-glucose laboratory. The body will simply reject it in its excretory system. Nothing will happen. Sometimes some enantiomer is beneficial to health, and the other enantiomer is poisonous. Poisonous. Therefore, in biochemical processes, selective enantiomers are required for a particular bioprocess. Many of the enantiomers have different smells. That also sometimes you find the smells are different. Sometimes their odors, not all, are sometimes different. I will cite several cases. Now I'm introducing, today's class will be just to have an insight into all types of stereoisomerism and their classification. In optical variety, you can also find diastereomers which have different physical properties, but they are not mirror images. Their boiling points, melting points, all are different, like geometrical isomers. Have same physical properties as enantiomers. They're mirror images. They're not mirror images. So, well, I'll give you examples of each type. First, I will begin with geometrical to give you an example, which Samitha, you were talking yesterday about it. You know, I have already told, you already know. So an example of geometrical isomerism, they do not show any optical activity. They do not respond to PPL. And supposing you have BU2 in, and each of the sp2 carbon of the double bond is bonded to two different groups. For example, here methyl hydrogen, here methyl hydrogen. These two can be same as these two, or they can be different, altogether different. But the moot point is these two groups will be different, these two groups will be different, not same. If one of the sp2 carbon has two identical groups, either CH3 or HH, such a molecule is unfit to show any kind of geometrical isomerism. Why? Because each sp2 carbon in this case is a stereo center. These two are stereo centers. If you make a switch in the language of stereochemistry, switch is not electrical switch. Switch is to interchange between two groups at a particular stereo center. So if you remove this methyl group from its hole and remove this hydrogen atom from its hole and interchange, just interchange at a particular, not both, at a particular stereo center, then what will happen? This methyl will take the position of hydrogen and hydrogen will take the position of methyl. As a result, you are not getting any mirror image. Instead, you are getting another diastereoisomer or diastereomer or stereoisomer which are non-superimposable. If you try to keep one fixed and bring the other one and try to match, superimpose, bond by bond, atom by atom, you will fail. Because if you bring this methyl and this methyl will be matching, but this methyl will not match with hydrogen. This hydrogen will not match with methyl. So you cannot superimpose them. So if in any way they are not identical, structure is same, both are butene, but they are non-superimposable. Had it been identical in all respects, they would have been completely superimposable. Butene. Therefore, you have to give an adjective to distinguish between the two stereoisomers which are commonly called geometrical isomers because their geometrical relationship, methyl, methyl, they're lying on the same side. Here, methyl, methyl, they're lying on the opposite side. That is why they were called geometrical isomers. Nowadays, they are called EZ isomers because one of them is E, which was called cis, is now called Z. This one, when the identical groups are opposite to each other, they're called trans. Now it is called E. We'll talk about the determination of Z and E in all different varieties of compounds when the groups are completely different. Completely different. We will try to, we will learn at the appropriate time, but not now. So these are stereoisomers. These are geometrical isomers. These are diastereomers. They cannot show any optical activity. If you pass PPL, it will not respond. Because we'll be knowing in a very short time from now what is the requirement for a molecule to show response to PPL and hence becomes optically active. That we will know. Well, supposing, just see how interestingly, supposing these two groups are same. Supposing you interchange between these two. This molecule is not at all a candidate to show any stereoisomerism. Because if you interchange between these two dissimilar groups, bring hydrogen here, methyl here, you will definitely ensure superimposability. You bring this, make upside down, just tilt it to the other side, you will find the two are superimposable. Just take this in your hand and make upside down. The methyl will go the other side and then bring to the first molecule. They are superimposable. Then they are one and the same. They do not have any different adjectives. No adjective at all. So we will be knowing that a molecule to be a candidate for geometrical isomerism should have the two groups attached to the sp2 hybrid carbon, because geometrical isomerism is shown in compounds having double bonds, C double bond C, C double bond N, and so on and so forth. You know about that. Now coming to, coming to enantiotropism, the enantiotropism and optical isomerism, in general optical isomerism, I will be introducing optical isomerism now. These are, dissymmetric molecule. And obviously they are three-dimensional, non-planar. They are non-planar. A double bond compounds are planar at the double bond site. They are planar. So these, and they need to have an sp3 hybrid carbon or nitrogen or oxygen or sulfur. And mostly we will be dwelling on carbon. But I will give you examples where sp3 nitrogen will also show optical isomerism. Oxygen also, sulfur also. You need an sp3. Now the main reason for a molecule to be dissymmetric, and most importantly, dissymmetric molecule, dissymmetric, what is the spelling? D-Y or D-I? Dissymmetric. Who can say?
Sir, DI.
D-I. D-I. I will give you extensive notes and yeah, DIS, SS. Oh, SS, single M, I doubt. Let us, Google Jindabad. Google has made our lives so very interesting, sometimes very, very frustrating. If you guys, ask anything about health, then it will drag you to cancer. So it is very difficult to handle, you know. Mm. Therefore, health related things one should not rely on the Google's, experts. They all give conflicting. One doctor telling something and the other doctor will be telling exactly the opposite thing. That's the beauty. Therefore, the English saying doctors differ. No, double S and double M. So here I have made a mistake here in the original file. So dissymmetric molecule, sorry, molecule has a non-superimposable, that's the beauty. I will show you mirror image isomer, and that is called enantiomer or optical antipode. If molecule is dissymmetric, then such a molecule will have another form which can be obtained by becoming a molecular surgeon by switching between any two groups at that particular stereo center. This time the stereo center is called the chiral center, asymmetric center. So, let me tell you first, the dissymmetry can be due to a presence of chiral centers or atoms, chiral centers or asymmetric centers or chiral axis. Now, whatever may be the case, anyone who is watching from the YouTube, how are you feeling? Can you just send a hi message in the chat box to make me feel little more encouraged? Because I thought that this topic, which is really interesting and hardcore, particularly concept based, and those who are aspiring for advanced IIT advanced, they should have much more information than what is stipulated in your book. Much more than that. That is why I thought of making these series of lectures public. Now, whatever may be the case, dissymmetric, DI, molecule, how will you know that a molecule is dissymmetric? has no or absence of a plane of symmetry, this is represented in the group theory symmetry properties notation sigma. B, center of symmetry, is also called inversion center. This is represented by I, and C, alternating axis of symmetry. I will explain to you everything, whatever best required. Alternating axis of symmetry. Some people call it improper axis of rotation. Improper axis of rotation. This is designated by S subscript N. Interestingly, there are 4 elements of symmetry. I will today discuss each one. But for a dissymmetric molecule, whether the molecule has one or more chiral centers, asymmetric centers, that means individual atoms which are asymmetric, or it has a chiral axis. With respect to that axis, it is dissymmetric. Doesn't matter, but it will be not having any one of these 3. If it doesn't have a Sn, you will never find a sigma, you will never find a I. If you don't find an I, you can never find Sn and sigma. The moment one of them stays, but conversely, you may find I, you may not find sigma or Sn. So in any of them is present, let me write down, if any one of these is present in a molecule, any one or more present in a molecule, it is symmetrical, dissymmetric way, and hence achiral. It's called achiral and optically inactive. ता धीरे PPL pass kale, nothing will happen. And in this context, I would like to tell you all planar molecules, even if they have different groups, substituents are achiral, because the molecular plane, the plane passing at the midpoint of all the atoms in that particular plane, that is itself the mirror plane or plane of symmetry. I will talk about that in a short while from now. All planar molecules are achiral and optically inactive, as they possess sigma. Because I will not be every time writing plane of symmetry, because the plane of symmetry is designated as sigma, inversion center as I, and Sn is alternating axis of symmetry. Interestingly, the 4th element of symmetry which was not included, the presence of that will make a molecule dissymmetric and hence chiral. Here, let me tell you that dissymmetric molecules, they are chiral molecules. These are called chiral molecules. the presence of, interestingly, the presence of another that is called only axis of symmetry, n-fold axis of symmetry, a normal axis of symmetry. That is also n-fold axis of improper axis. N-fold axis of symmetry, and that is written as Cn. Cn makes a molecule chiral, dissymmetric, and hence chiral. Now, I will tell you everything. Without wasting time, I will give you examples of all these elements of symmetry. Let me tell you elements of symmetry. And when you a symmetry operation is made, with any element, so the one I pointed out, if the form is repeated or becomes indistinguishable, then it is a symmetry element. The molecule, the more symmetry element a molecule can have, the more symmetrical it becomes. For example, fullerene C60 has the maximum number of symmetry elements. It has sigma, multiple sigmas, I is always one. Whether one I or no I cannot be second in an entire molecule, I'll tell you. And multiple SCN, multiple SN, that can be possible. But only I can be only one, if at all there is I. Or Jack and I'm so sorry. I'm just kidding. Now, I will now talk about sigma. What is sigma?
Plane of symmetry.
Plane of symmetry.
I'm writing in short PS. I am just showing you a three-dimensional picture of tetrahedral carbon having groups. This is called the Wage formula, where the three-dimensional, because all the bond angles are 109 degree 28 minutes. So to show them in pen and paper, we have to produce or draw two wedges. These are called the wedges having bold face. The other one is a normal line. The other one is a broken line. That doesn't mean that the bond is broken. This broken line indicates that the bond is below the plane. And this bold faced line called wedges They are lying above the plane of the paper or plane of my screen. And the normal line is lying on the screen, on the paper. So supposing we have hydrogen, at least two groups or atoms bonded to the sp3 carbon are identical, at least two. Then the third and fourth might be different. This may be CH3, this might be chlorine. But you can imagine a theoretical plane passing through this carbon, and this chlorine. So those atoms and groups, they are lying on the imaginary plane. This is called the mirror plane, which is imaginary. Sigma plane, we call this sigma plane or plane of symmetry. It's a plane of symmetry. Why? Because if two groups are different, and if you pass the mirror plane through those two different groups along with the central carbon, that becomes the mirror plane. And you know from physics that if some point sits on the mirror plane, then its image is also there on the object itself. So any group sitting on the mirror plane, the image also will be there then and there. They will be overlapping with each other. And this side hydrogen, this side hydrogen. And hence, this is, and if you reflect the molecule with respect to this imaginary mirror plane passing at some midpoint, if the reflected image will be superimposable, indistinguishable with the original form, then that is called an element of symmetry. And in this case, it is plane of symmetry. You understood? This
Yes, sir.
Yes, sir.
this will be reflecting with this, its image will be falling on this image will be falling on this. So the new reflected structure, I mean form, don't say structure, form is superimposable with the original form. Therefore, we consider this as a plane of symmetry. So if at least two groups are same, then the molecule is achiral, it is symmetric. Once there is a plane of symmetry, it is achiral and optically inactive. It is optically inactive. But the moment we make all the four groups different, for example, I will just not change much. Here it is H, but on the other side, it will be something else. For example, it is OH. So can you ever imagine any plane of symmetry in any, whether you pass through this or pass through this or anywhere, can you find a plane of symmetry which will divide the molecule into two mirror image halves? Can you find any sigma plane is not a sigma plane? Because on this side hydrogen, on this side OH, they are not the reflection of each other. The reflected image will not be superimposable with the original form. If you pass through this hydrogen, carbon and OH, then also methyl will not image with chlorine. So this is a dissymmetric molecule because it does not have a plane of symmetry. Therefore, I have written not a sigma plane. So this is a dissymmetric molecule because it doesn't have a sigma plane. If you find one diagnosis, supposing you are a doctor, you know that there are several symptoms for a disease. And if you find one symptom, without looking to the other symptom, you can say that this is the disease. So if there is no plane of symmetry, there cannot be a SN, there cannot be any I. There cannot be any. I will talk about I, the wife of Oja, very soon in some particular case. And in this case, now this has turned into a stereocenter. Hence, it is a chiral molecule. And such an atom is called a chiral center, stereocenter. And that stereocenter, in this case, called a chiral center. Some people call it asymmetric carbon atom. So such a molecule is a candidate to show response to PPL. If you pass PPL to pass through this molecule, maybe it will rotate to the right and you can brand it as D or plus. And you make one switch, making one switch. Switch here, that is interchange between any two groups. About the stereo center. In this case, the stereo center is chiral center or asymmetric center. Converts one form, whatever you have taken first, to its enantiomer, to its enantiomer, enantiomer, or mirror image form. I will be showing you here how by making any one switch, interchanging between hydrogen chlorine, interchanging between chlorine OH, interchange between methyl OH, whatever, but one switch. Bond breaking and bond making, that you have to do. Then you will feel that you are not generating the same molecule, because dissymmetry means its mirror image will not be superimposable. And if one is D, the other one is L. I'm showing you in a model because I have a model box. I was trying to, because if you guys are very smart, then without models also I can go far. But sometimes it is really interesting to visualize through models. Now see, you can see that I have connected four different colored balls. The center one is carbon, which is sp3 hybridized. The bond angles are all 109 degree at 28 minutes. One is a white ball, the other one is a blue, the third one is red, and the fourth one is green. So this carbon is called an asymmetric carbon atom. So let me write down what is an asymmetric carbon atom or asymmetric center. It may be a nitrogen atom also. I will talk about that later. Carbon atom bonded to four different groups. Then only it will be dissymmetric. And you cannot get sigma, you cannot get I, you cannot get Sn. This is a chiral center. Particularly chiral carbon center. Chiral center is normally carbon is taken in exclusive discussion, carbon is taken. But in rare cases, I will tell you nitrogen, sulfur, they also show dissymmetric molecules which are chiral, chiral. 4 different groups, and you cannot find any of the 3 elements of symmetry. Now see, this molecule, supposing you consider green as OH, red as carboxyl group COOH, and blue as methyl, and hydrogen white, always we take white as hydrogen. So remember, red is carboxyl, green is OH, blue is methyl, and white is hydrogen. So such a molecule is called lactic acid. I will show you lactic acid, which is obtained from the milk. And that is responsible for the curdling. I mean, the process where milk is converted to curd. Lactic acid is responsible to coagulate it. Anyway, now I will have identical case, exactly identical molecule I will create. Same for white, red, green, and blue. Let me first check. Hiding from you, let me check whether they are superimposable or not. Now see, these two are identical. They are superimposable. देखो ऊपर यार ग्रीन तार भी ग्रीन, डाण पटे यार भी रेड तार भी रेड, मो आड़कू व्हाइट, मो आड़कू यार भी मो आड़कू व्हाइट, एवं तुम आड़कू ब्लू तार भी ब्लू. सो एटा को जानी करी मो आइडेंटिकल करिछि, एंड गोटा को मु हाथ रे रखी देली, एमथि छाड़ देली, हाथ लगेलिनी. And I will ask you, had you been in an offline class, I would have given you the task to switch, interchange between any 2 groups. Now, if you trick me someday in some year, maybe I was teaching in an offline program, a guy, maybe not knowingly, unknowingly, and it was proved to be a trick. He did some action. I thought that he did switch once, but he didn't do anything. Then I started in a dramatic way. Now see, this form and this form will not be superimposable. To my utter dismay and utter shyness, the 2 became superimposable. Then the guy was laughing, smiling at me. Now, if you really interchange between any 2 groups, now I am interchanging between, say, red and blue, or say red and green. I broke the bond and I remake the bond. Bond breaking and remaking, calling. That guy must have broken. Actually, he was breaking. But while remaking, he forgot, because nobody will play such tricks at this early stage. And unknowingly, by mistake, he made the bond then and there. I mean, in the same place, not the real switch it made. I made a switch. I don't know. While talking, if I had, bond broken, but bond making done in the same place means doing nothing. I have really switched, then I will compare between this one and this one. In whichever manner I will try, supposing I will keep green up, and red left. At least two will superimpose, but the white will match with, will fall in on blue, and blue will fall on white. Same thing will happen if you try to match the other two balls, other two colors, then the remaining two colors will be just the opposite. You can never, ever superimpose the two. If you cannot superimpose, they are not identical. They are space isomers. The relationship between the groups and or atoms about the center, stereo center, they are different. That is why they are not superimposing. And that, fortunately, is responding to a typical light called plane polarized light differently. If one of them will be rotating to the right, its enantiomer will rotate to the left. We cannot know which one is which unless we perform the experiment. In a polarimeter, I'll talk about the details in every case. Now, carbon atom bonded to, and for making one switch, I have already written, so there is no necessity of writing again. I am showing you because we will be showing in pen and paper, and it should look nice. A lay person can understand, should not trick, not really trick, but the optics, I mean, I'm not physics optics. I'm using the word optics in a literary sense. Supposing this is H here, this is methyl here, this is carboxylic acid here, and this is OH here. This is called lactic acid in trivial language, but we can call it 2-hydroxypropanoic acid. And you know, if we interchange, we can interchange between these two or these two or these two. Whatever the switch may be, you are generating its mirror image. I forgot to tell you. Instead, you don't try to make superimpose. You cannot. Instead, you can establish a mirror image relationship. Try to manipulate the model in your hand. Don't make or break, but manipulate by rotating in your hand. So if you'll find that the two are related with each other as mirror images. But they are not superimposable. So they are enantiomers. They are different in only one physical property called the response to ppm. Sometimes their smells are different. If they are biomolecules extracted from plants, sometimes their smells are different. And one of them may be good for health, the other one may be bad for health, doesn't work at all. Sometimes it becomes a poison. Now, for getting a good view, let us exchange between left and right so that we can jolly well put a vertical mirror. Otherwise, you have to manipulate the model, which is not possible in drawing. Therefore, it is customary to interchange between left and right. But that doesn't mean that you have to always interchange between left and right. So COH will be plucked out from its hole and will be put here in the hole of methyl. Methyl will be plucked out from its hole and it will be put in the place of, this is COOH. And the other two, let it be same. So deliberately we have exchanged between left and right to look like they're mirror images because you are taking a vertical mirror. But in principle, any switch. So if one is, these are lactic acids. I do not know whether this is D or this is L. I'm writing DL pair. First of all, let me write down. If one enantiomer, guys who are watching from the YouTube, if you can follow my classes, I think max seven classes will be required, maybe of 2 hours duration each. It will be really a challenging job for guys to continuously sit for 2 hours at this stage. But maybe since it is for those who are aspirants for IIT Advanced at least, or they have to do that. If one enantiomer rotates PPL, let me write down what is PPL, plane polarized light. Then I will further explain what is plane polarized light. To the right, it is called D or plus. D stands for dextrorotatory. And the other enantiomer rotates the PPL to the left. It is called small l. Remember, small d, small l. Or minus. L stands for LAVO. In English, British English, LAE. In American English, simply LEVU. LAVO rotatory. L. This D and L are relative configuration. Which can be determined experimentally. In a polarimeter. Polarimeters are kept in dark rooms. Polarimeters. And let me tell you what is PPL. I will give you a note on PPL later, but let me tell you what is PPL. You have to use a monochromatic light, say D1 light of sodium, 5890 and 90 angstrom. 5890 angstrom is the D1 line, the yellow D1 line of sodium. This is monochromatic. 1996, what? Anybody who remembers? 5890. D2096. Yeah. That particular monochromatic radiation D1 line, but the light waves, they vibrate in all possible planes. The wave front, it travels in all possible planes. this one, this one, this one, this one. But when that monochromatic light is passed through a particular prism called Nicol prism, that Nicol prism is made up of a pure calcium carbonate crystal, transparent crystal. Then on the other side, the waves, they only travel in one plane, say vertical plane, one plane. So they were traveling in multiple planes, but after passing through this Nicol prism, all the light waves, they travel in one plane. That is why plane polarized. Different planes merge into a single plane where the wave propagates. So that particular one plane light, a single plane light, is called plane polarized light. When that passes through an optically active compound, dissymmetric compound, I told you that planar molecules can never ever be dissymmetric, because whatever may be the different substituents present in the plane, but the molecular plane will be the mirror plane. The half of this sphere and other atoms are considered to be sphere. The same atom lying above the plane and same atom lying below the plane, so they are chiral. But only the three-dimensional molecule having sp3 centers, they may or they may not have dissymmetry. Dissymmetry is tested by the absence of these three elements of symmetry: sigma, I, and Sn. Sometimes the presence of Cn, the fourth element of symmetry, makes the molecule chiral. That's the beauty. I'll tell you in, maybe may not be today, maybe some other day I'll tell you. Polarimeters are responsible. These are therefore called relative. If one is D, the other one is L. But we can find their absolute configurations R or S by looking to the picture, drawing, model, drawing. We can do that. So before we go further into optical activity, which we will be proceeding further. Okay, let us little go further. First of all, let me tell you a term called a racemic mixture. Sometimes or DL mixture, or sometimes racemate. 50% of D or plus and 50% of L of the same compound. One enantiomer 50%, the other enantiomer is 50%. Makes the mixture optically inactive. Due to external compensation. Due to external compensation. So still I maybe I request or I urge, and the guys who are watching from a distance remotely in YouTube can have a word with me. Hello and hi. Just tell. You can also write Merry Christmas. Also, you can wish me so that I'll be encouraged. Well, now, because supposing you take a mixture of lactic acid 50% D-lactic acid, 50% L-lactic acid, and pass BPL, it will go straight. Why? This 50% D will be trying to rotate to the right, and to the same extent, the other 50% L will be trying to rotate to the left. So they will cancel, they will compensate each other externally. Because we will, later on, we will learn a term called internal compensation. Within the same molecule, there will be cancellation or compensation. Here, we have 50% D, 50% L. Such a mixture is called a racemic mixture. Often, when we prepare lactic acid by some chemical method, we land at a DL mixture. Whenever a new chiral center is synthesized, Rudra Narayan Sahu, Rudra, you have wished me Merry Christmas?
Yes, sir.
Nobody is doing. So why not the one joining my Zoom class? Okay. And you have a cake, I think a cake wrapped in a box, right? I will open
Yes,
it
sir.
and I'll cut it today. Yes, what I was saying, Sami?
Sir, lactic acid preparation and lab.
Yeah. Whenever we prepare in some synthetic methods a new chiral center, you will find always that there is a DNL mixture. You get a racemic mixture. But the two can be separated, although difficult. To separate enantiomers is hell of a job because all their physical properties are identical. No fractional distillation method, no fractional crystallization method, no fractional evaporation method will helpful because their physical properties are same. So, but they are separated in an indirect method which we will know. Let me write down before I forget. Diastereomers. About diastereomers, we have learned in geometrical isomers. So far, we have not learned diastereomers, which are not mirror images, but they are optical isomers, but not mirror images. They are not planar. Geometrical isomers are mostly planar, at the site of the double bond at least. But this is sp3, diastereomers can be separated easily by supposing fractional distillation, etc., or other physical methods. As their physical properties are different. But enantiomers, those which are mirror image isomers, the enantiomers cannot be easily separated, but they can be separated. They are not, they are there, but you can permanently separate them unless the enantiomers are also conformational isomers. We'll talk about that later. That is because so many fascinating things are there. And at the end, the last two classes, I used to say there will be wedding between configuration and conformation. Say one of them will be bride, the other one will be groom, and we will have a ceremony, with a wedding ceremony between configuration and conformation, where the configuration is to be fixed and we change the conformation and see the stability. And in some extreme cases, the conformations are also enantiomers. These are called conformational enantiotropism. We'll talk about that later. But enantiomers cannot be separated easily. They are separated by special techniques. That is called, we will study that in a particular heading called resolution of a racemic mixture. We'll study that later. Now, before we go, let me tell you, supposing these two are now mirror images. Okay? I will keep one and make once again a switch to any one of them. Then what will happen? Tell me. On the same one. That means I made two switches. One switch to make the enantiomer of the first one. And the second switch when we do, maybe first switch was between red and blue, the second switch is between white and green, doesn't matter. If we make two successive switches at a particular stereo center, chiral center, then what will happen?
So superimposable.
Yes. You will arrive at the same form. You will arrive at the same form as if nothing has done. As if you have done nothing. You have just wasted your valuable time. So making two or any even number of switches does not change the configuration. That phenomenon is called retention of configuration. The configuration is retained. You will see in during the course of reaction, you change once the configuration is changed from R to S. I have not yet introduced R and S. And again, you made another inversion. I mean, I have also not introduced inversion, which I'll tell now. Then ultimately the configuration will remain the same. So if you make two or any even number of switches, then you are not changing the configuration. If the molecule is same, then the form will be identical. And if you make one or any odd number of switches, 3 switches, 5 switches, then you are converting one enantiomer to the other enantiomer. That is called inversion of configuration or Walden inversion. Let me write down that by making one or any odd number of switches, like 3, 5, what will happen? What shall I write here?
Will change.
That is called configuration is inverted. And this phenomenon is called inversion of configuration. D will be converted to L. L, if it is L, it will be converted to D. And later on, we will write if it is R, it will be converted to S. And if it is S, it will be converted to R. These are absolute configurations which we will be learning very soon. These are relative configuration. But if you have a prior knowledge that lactic acid, R lactic acid is L, laboratory, then you can write down. Supposing I know the literature in standard literature of optical activity, different known compounds, they have the data. R something is L and hence S something will be D. If a compound is unknown to you, you cannot say because you have written first in the left side it will be D, in the right side. When I was a beginner in the equivalent +2 level, I don't think in our time +2 level was having stereoisomerism. We were exposed to stereokind is in only in +3. I mean that time it is called BSc. I had a belief that in whatever is written in the left side it is D and whatever is written in the right side it is L. No. Whatever is written in the left side, you can just look at it and say whether it is R or S. I'll tell you the rule, the CIP rule. But you cannot say whether it is D or L unless you know prior to, this, R something, R lactic acid is L or minus. Then you can write down before, the left one is R. You find from your look, from applying the rule, you know that R lactic acid and you know that it is L. So you can write L in the left side, minus. Right? So there is no fixed correlation between relative configuration and absolute configuration. I will write that later. Lactic acid, I know R lactic acid is really L. But R methyl lactate, just an ester, COOH will be COOMe. Only slight change, not at the first atom, but at a further distance, miles apart. You are making a little bit of change where the configuration R remains R as per rule. But when you go to the polarimeter darkroom, it might have an opposite rotation. So methyl lactate R is D, while lactic acid R is L. And if one is L, its enantiomer is D, and vice versa. So we'll talk about that later. But I was interested to write that this is called inversion of configuration. So by making 2 or any even number of or any even number of switches, what will happen? What will happen?
No inversion will occur.
What is that called? I have already spelled out many times. Om, Sami, anyone? The configuration will remain the same. And that is called retention of configuration. Retention. That is inversion, retention of configuration. That means D will remain as D, L will remain as L. This is, and in the absolute case, R will remain as R, S will remain as S. No change in the configuration. When we are talking about bond breaking and bond remaking, we are playing with configuration. It's stereoisomerism, but you are playing with configuration. You are changing the configuration by becoming a molecular surgeon. Bond breaking and bond remaking. Retention of configuration. Now, on the other hand, I will just introduce something about conformation. Where you have to make some, supposing I am a person, I'm not going to make any operations. If I make a surgery here, I cut from my neck and just invert it and again stitch it. Then I'm changing the configuration. The first person and the second after surgery, they are not superimposable. Its nose will be its nose will be on the back side, my nose will be on the front side. They are not superimposable. They have changed their configuration. But the same person without, touching the seizures, no surgery, nothing. It was just dance. Now I am in this pose. Some of you take a picture. Now second time I am in this posture. Take a picture. Are the two superimposable? Are the two this posture and this posture? Are they superimposable? No.
No, sir.
No.
Then you are making a change in conformation. And they are conformations or rotamers or conformations. Some of them are stable. The molecules love to remain in that particular conformation because of its stability, lower energy. So such conformations are called conformational isomers. For example, I will draw the sawhorse projection formula of ethane. Don't worry, I'm just introducing. Today class is introduction. And I tell you, those who are watching from the YouTube, we have already fixed up continuous 4 days classes during the same time, 3 to 5. Today, 25th, Merry Christmas, 26th, 27th, and 28th. Same 3 to 5. But there will be a break. 29, 30, 31st will be break. And we will resume from 1st. But from 1st onwards, since there will be school, we will be having our program at 6:30 to 8:30. So those of you who are watching from a distance in the YouTube can watch the video later when you are free from your coaching and other systems, other learning houses. Then only you can get into the depth of stereochemistry. Because, in the advanced IIT level, stereochemistry is very important. How the reaction is moving, how this configuration is changing, whether the conformation is changing or configuration is changing, or both are changing. Sometimes I told you that conformations are also optical isomers. They are not configurational isomers, but they can be optical isomers because they lack symmetry. They are dissymmetric. So I have only touched a single point on dissymmetry having one chiral center, and that too chiral carbon. In the tomorrow's class, we'll be talking in details about optical isomerism having multiple chiral centers. Before that, we will discuss how to determine the absolute configuration R and S for one chiral center, the Fisher projection formula. From the Wade's formula, there are 3 Wade's formula I will tell you today, and how to transform into another simple formula called Fisher formula easily. And looking to the Fisher formula, you can just identify whether the absolute configuration is R or S. And then multiple chiral centers, 2 chiral centers with a possible symmetry element. Then 3 chiral centers with multiple chiral centers. The formula to find the number of optical isomers, the number of mesoforms which are optically inactive, because they might have 2 chiral centers, but that particular molecule lacks dissymmetry. It is symmetrical because of the presence of something, some of the 3 elements for which the other partners, they are they are chiral, but that particular isomer is achiral. Doesn't respond because it has a plane of symmetry or I or Oja and SN. So we'll have a fascinating discussion as we proceed with this. That is the reason why I thought of having a public program. Supposing this is the Sohor's projection formula, hydrogen, 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 and this is hydrogen, hydrogen, hydrogen. This is a carbon-carbon bond. This is a carbon. This is a carbon. And this is all angles are 109 degree 28 minutes. It looks like as if it is 120 degree because it is a projection. It's not a 3D. It's a projection, so it will look like as if it's 120 degree, but actually it is 109 degree 28 minutes. So when these two hydrogens, they are on the same line, they're eclipsed, like your solar eclipse, lunar eclipse, they're on the same side, and these two are also eclipsed. These are two also eclipsed. So this conformation is called eclipsed conformation. The name is eclipsed conformation, which is not stable. The molecules, they do not exist in this conformation because there will be a lot of strain. I will talk about different types of strain, torsional strain, angle strain, dipolar strain, van der Waals strain, so many types of strain we will know. This is because the bond pairs are close to each other. They will have a repulsion among their electron clouds that will make it unstable. But if we rotate, I'm showing you here so that you will have a better idea of what is going on. We will not be doing anything. Simply rotate. By rotating my hand, I am not going to change my identity. The identity is configuration. I mean, stereochemical identity is configuration. But stereochemical conformation is not the real identity because the conformations, conformers, conformational isomers, they are interchangeable. They remain at equilibrium with each other. You cannot separate one conformation from another conformation. Just like you were able to separate D from L by some special technique. And the two independently can exist for years and years without racemization. But when we talk about conformational enantiotropism, in that case, there will be a slow racemization, otherwise not. But conformations of the same configuration remaining same, but it has multiple conformational isomers, they are always interchangeable. But in this case, ethane, 99.999%, nearly 100% remain in the staggered form. When you make a 60-degree rotation, now see, this is what we call the eclipse conformation. This they are eclipsed. This eclipsed. This eclipsed. Three pairs of hydrogens, they lie eclipsed, parallel with each other. So it is unstable. But if you make a 60-degree rotation, just 60 degree. So the angle what we find to change is called the dihedral angle. Dihedral angle is a 3D angle. That is the angle between two planes. One plane containing, supposing this hydrogen towards you, supposing this is called H1. This is carbon 1 towards you and towards me carbon 2. So one plane carrying hydrogen 1, carbon 2. And the other plane carrying carbon 1, carbon 2 once again and the hydrogen towards me, that is H2. So in this case, the dihedral angle is 0. And if you keep one carbon fixed tight in one hand and rotate the other, that means this plane remains the same, but this plane becomes 60-degree apart, and that is a solid angle called the dihedral angle. When you give a 60-degree turn, don't worry, I will give you notes because I know I am teaching to beginners who are aspirants. So I never ever teach revisioners. It will be a very unpleasant experience unless a person is very, very peasant, not the diseased, peasant, having a strong sense of peasance you will be repeating. Otherwise, it's very difficult for me. I never do that. So if you make a 60-degree rotation, change the dihedral angle from 0 to 60, you will find now you find 3 pairs of hydrogen come opposite to each other. Not the same 3 pairs which were eclipsed. Other 3 pairs. Supposing these 2 are eclipsed, now this and this will be opposite. This in your side and this in my side opposite. And this in my side and this in your side will be opposite. So immediately with 60-degree rotation, eclipse conformation will be converted to another conformation which is stable, the most stable one, where this is called the torsional strain or bond opposition strain. Bonds which are on the same side, they push each other, they repel each other. This is called the bond opposition strain, or the torsional strain is maximum in the eclipsed conformation, but that is greatly relieved when you rotate 60-degree. And if you turn it more, then it will be heading towards again eclipsed. The stability will further decrease. So every 60-degree rotation about the CC single bond will alternate the conformation from eclipsed to staggered, staggered to eclipsed, eclipsed to staggered, and so on. Now I'm showing you these are the conformations. Now see, the front one I am keeping fixed, and the rear one I am changing. This was H1, this one H1. This is H2. Now H2 is here. 60-degree rotation. Here the phi is 0, dihedral angle is represented by phi, and this is phi 60-degree. Here these 2 are opposite, these 2 are opposite, these 2 are opposite. So this conformation is the stable form, that is called the staggered conformation. And in fact, about 100% of the molecules in the room temperature remains in the staggered form. But if you raise the temperature, because the energy gap, the enthalpy change between these two is about 5 to 6 kilocalories per mole. So if you raise the temperature, then some of the molecules, they will go to the higher energy eclipse conformation. Otherwise, at room temperature or in the vicinity, nearly 100% of the molecules remain in the staggered form. Actually, this is a staggered conformation. Conformer. This is a conformation, not a conformer. It is an unstable, highly unstable. This is highly stable, and in between the stability will vary. The most stable is this, and the least stable is this. And in between the angles, whatever angle you may change from 0 to 360, you will find staggered followed by eclipsed. And we will be learning the configuration, the conformation of butane and other compounds, cyclohexane and other cyclic compounds later on. What I wanted to tell you that while we change conformation, we do not bond break and bond remake. Simply rotate carbon-carbon single bond. These two are non-superimposable. Aku nekri ta upare pakeibo kebe superimpose habani. So if the two forms are non-superimposable, whether due to surgery or due to hip hop, Odissi, Kuchipudi, whatever may be the case, they are stereoisomers. This is conformational isomers, and that is configurational isomers. And configurational isomers has two parts, optical and geometrical. Geometrical requires a carbon-carbon double bond, a double bond, planar, so that we can have two different forms, non-superimposable forms, and we can call it one Z, the other one is E. And if it is sp3, it has got one chiral center or a chiral axis. I have not talked about chiral axis. Then it will be optically active. It will respond to PPL. Now, only rotation about CC bond makes different forms non-superimposable. In fact, there are infinite number of conformations, infinite number. And some of them, which are called conformations, all are conformations. Out of which some are stable. In this case, you find one is stable. But in other cases, you'll find more than one is stable. For example, in butane, you'll have two stable forms, Gauss and anti. In cyclohexane, you will find skew boat and chair. So, conformations out of which some are stable, which are called conformational isomers or conformers or rotamers. So therefore, these are also called rotational isomers. Some people call it rotational isomers. Conformational isomers are sometimes called rotational isomers. To make things look easy, rotational isomerism. So there is another way to express that is called the Newman projection formula. Let me introduce. This is much easier to make a circle and then put a dot at the middle center, then draw three bonds. This is one carbon, and the rear carbon is not visible. Because supposing an opaque disk, circular disc. So the rear carbon is not visible, and the bonds up till the end of the circumference is not visible. So the visibility now is above this. So since we cannot have a real, supposing in the eclipsed mode, if you take the picture while you are eclipsed, then you can't see. You have to tilt yourself. I used to funnily say, Tike, तुम्हें कौणेकिरी चाहिए कौणेकिरी चाहिए तुम्हें पछपटर एक्लिप्स्ड हाइड्रोजन को देखि पारिबो अथवा जदि सेही तारी सिधारे रहिबो if you remain at one line with the eclipsed hydrogen, then the rear hydrogens are not visible, will not be visible. ସେଥିପାଇଁ ଏଇଟା ହେଲା the presentation, and the rear bonds are not visible up to the circumference level because it is taken to be a opaque disk. So this is the way called the Newman projection formula. It's very interesting, where the dihedral angle is 0. This is eclipsed. And supposing we keep the front fixed, anyone you can put fixed. and rotate the rear one, and it will come to the staggered here. Supposing this is H1 and this is H2, H1 is fixed, but H2 has come here. So there is a dihedral angle, which is a solid angle, will be 60 degree, and this is phi is equal to 60, and this is staggered. So these are the two forms of representing conformation of an acyclic compound, whether it is by sawhorse. You know what is a sawhorse? Just this is an inverted saw. No. Supposing here you put a wooden base and do some, carpentry work. So this saw, it looks like a horse, and this saw, this a wooden plate is a wooden base is kept here, and carpentry work is done here. That is why it's called saw-horse projection formula. And this is called Newman. Newman was the scientist to further simplify, to represent the conformation having two carbon atoms. So we are almost at the end of our program, but let me tell you, coming back now to optical isomerism in details. Not details, continued. Many things I have already told you, continued. One chiral center first. First chiral center, then chiral axis. Obviously, when I write one chiral center, it means a chiral center. One asymmetric, and that to carbon. Now, ways, there are three ways formula. The first two are similar, which I have already drawn. These wedges, which are shown by bold faces, they are protruding out of the plane, above the plane. And this normal line is lying on the plane, and this is below the plane, the broken line. Supposing A, B, C, D, or PQRS, because C you may confuse as carbon. So, but the middle one is carbon. This one is carbon. This is PQRS for different groups. Then only it doesn't have a I, Oja, and Nati. Tinta, Kichinayar. So it is dissymmetric. Hence, by making one or any odd number of switches, you invert the configuration. Turn D to L or L to D, or turn R to S, I have not yet told. And I am not showing its mirror image, which I have already done. The other way is to just, I will show you, just tilt a little bit. Many books, they give this one. They tilt the model little bit backwards so that P also goes below the plane. This R, although remains below the plane, but tilted little upwards, but still remain below the plane. So this is another way, they are similar. And another one is most popular now. Any two normal lines will indicate those bonds are lying on the plane of the paper. And one is above the plane and the other one is below the plane. Supposing this is P, Q, R, S. The broken line below the plane and the normal line on the plane, and the wedges above the plane. So this particular wedge formula has a very peculiar name called the flying wedge formula. So far I fail to understand what is the historical background to name as flying wedge formula. This has become very, very popular. Now I'm showing you. Have you written down? This will be the end of our program.
Yes, sir.
And guys who are watching from a distance or will be watching, I'm sure many will watch later. Consider, if you are benefiting from this program, consider subscribing to the program. I mean to my channel, what I call SST Chemistry channel. This is in collaboration with our NGO trust that is called the Uranium. Now see, have a look here. I am showing you the first model where the white one is lying on the plane. Supposing this middle, you imagine a plane passing at the middle, carrying the white one. And the two which are towards me, the red and green, they're towards me. They're shown by wedges, solid line or bold-faced line. And the broken line is this blue one, which is towards you. The first wedge formula. The white one is lying on the paper. But you make a little tilt. Then the red and green, they are lifted little up, but still they are above the plane. The blue is tilted little upwards, but still below the plane. So this is the second one where there will be two broken lines and two wedges. But the first two wedges, one broken line and one normal line. It was like this, now like this. But if you try, you bring your palm and you can keep any two on your palm. That is one plane. I am keeping the white and green over on my palm. That is in one plane. You'll find one of the other will be lying above that plane, my palm. That is, this red one is lying above and the green one is lying below. So the green one here is Q, the red one is R above the plane, and in my palm plane, P and S are staying. So you can try with any other two. You can keep in one plane and you will find out of the other two, one will be below the plane, the other one is above the plane. So this is called the flying wedge formula. Tomorrow we will be knowing how to, what is a Fisher, or let me write down, from here we start, Fisher formula. Fisher, that is also Fisher projection, that is also a projection formula. We start from here. I will try to put a break. Maybe we can chit-chat anything other than study. But if I start Fisher formula, then it will be an endless program. So how did you like it, guys? And give me your feedback. Particularly, I am interested from all those who are watching from the YouTube source, or even the insiders like Om, Rudra and Sami. And unfortunately, the other guy could not attend because he is so naive. He cannot also impose any restriction on our activity. As I have already told you that this batch was initiated for the uranium awardee Rudra. And with a condition that as long as he sustains the same spirit as he was having for the last several years, the same spirit continues, then our program will continue. Otherwise, I will find, and then my granddaughter also joined. I also gave her an offer. She can also ask her doubts whenever she faces, but she opted no. Continuation, a continuous program will be more beneficial to her than a discontinuous doubts clearing session. And Om also joined with also a good level of aspiration, but he has to also give little more efforts to sustain. And guys who are watching, my programs are all meant for IIT advanced level. We start from the grassroots, from the very, very fundamental till depth. Okay, that's all for today. Happy Christmas won't do. Merry Christmas to all of you. Enjoy in the evening. I have one meeting to attend in the night time, so I'll be busy for that. Bye bye. I am signing out from the YouTube. Bye. See you tomorrow at the same time, 3 p.m. Bye bye. Hello, guys.